Hello guys, just today talk about beryl. Beryl belongs to the cyclosilicates and it's a very beautiful mineral showing hexagonal columns. So today in very brief, we shall be talking about the structure of beryl followed by its chemistry and something on its paragenesis. Beryl is an important ore of beryllium. We all know that, and probably it is one of the only ores of beryllium. So let us see what beryl is, what its structure is, and how it is formed. So as I told you, beryl is a cyclosilicate with its chemical formula or chemical composition as Be3Al2Si6O18. So if we take the Si to O ratio, it will be 1 is to 3, which is a typical of cyclosilicate. So if you have to draw the cyclosilicate, I'm sure you can draw it this way. You all are aware. So that we have this tetrahedra followed by then this, and this. So you can see here, we get a ring-like structure. And in this ring-like structure of these tetrahedra, the red ones, they are the silicon. So we have 1, 2, 3, 4, 5, 6. 6 silicon here. And then let us see how many oxygens are there and how many are shared. So here, this one is shared, second one, third, fourth, fifth, sixth. After that, we have 1, 2, 3, 4, 5, 6. So 6, 6, 12, and one is here in the central part. So we have 6 more. So we have 6 Si and 18 O. That makes the ratio to 1 is to 3. And then bridging oxygens we have 1, 2, 3, 4, 5, and 6, which will be shared half between two tetrahedra over there. So we have these as the bridging oxygen. Now this structure, which looks like a hexagon, it's very obvious, and the beryl is located, or it belongs to the hexagonal crystal system. Beryl is an important mineral in terms of its gem varieties also, and the very well known gem varieties are emerald and aquamarine. So these are two commonly used gem varieties. Now beryl occurs in granitic pegmatites, very coarse grained rocks. Apart from that, in many metamorphic rocks it is found, and it is often associated with tin and tungsten ore bodies, which are formed as high temperature hydrothermal veins. So its importance is in form of the hydrothermal deposits, and it's mined commonly as the ore of beryllium, which is Be3Al2Si6O18. So these are some of the gem varieties of beryl. So you have green beryl, emerald, aquamarine, maxis beryl, maxis type beryl, then bixibite, which is also the red beryl. Then you have the morganite, which is pink beryl, goshenite, colorless beryl, and heliodor, golden beryl. So these might be asked as multiple choice question across few competitive exams. Now let us look at the structure of beryl. The dominant feature in the structure are the hexagonal rings. Okay, they are the hexagonal rings, and these rings, they overlap each other to form hollow columns parallel to the c-axis of the crystal. I'm sure you are aware that in the hexagonal crystal system we have three horizontal axes, which are A1, A2, and A3, and C is the optic axis. And the column of the beryl, if you see here, most of you must have seen beryl in your labs. So beryl looks somewhat like this. This is a hexagonal column. And this hexagonal column, it runs parallel to the c-axis. C-axis, okay? So the dominant feature in this structure of beryl, they are hexagonal rings of SiO tetrahedra, and these rings, they form hollow columns parallel to the c-axis of the crystal. Now within the rings, two of oxygen atoms in each silica tetrahedra, that is SiO4 group, are shared by SiO4 groups on the either side. So they have a metasilicate ratio. They have a metasilicate ratio. And then what I just said, that two of the oxygen atoms in each tetrahedral, each SiO4 group, they are shared by SiO4 groups on the either side. Now in this structure which you are seeing right now, you can see these large circles which are the oxygen atoms. The filled black circles, they are the silicon, Si. I'll just write it for you. Sorry, this is silicon, this is oxygen. You can see how two rings are overlapping each other to form this kind of a structure. And then the red dots, they are beryllium, and the green dots, they are aluminum. So you have Be2 plus and Al3 plus here in this structure. Be2 plus and Al3 plus. So if you look closely at this structure, let me just clean it for you. Now, if you see here carefully, then you can find that the between the rings, see, one ring is this, the other one is this one, which I have just put two red dots. Between those rings, you can find the beryllium and the aluminum ions. The beryllium ion, the Be2 plus, Be2 plus, it shows no tetrahedral coordination. It coordinates tetrahedrali with four oxygen atoms. Four oxygen atoms, the Be2 plus. You can see here 1, 2, 3, and 4. While Al3 plus, it coordinates octahedrally. It coordinates octahedrally with 6 oxygen atoms. Okay, this is the structure. So the Be2 plus, the ionic radius of Be2 plus is smaller than that of the Al3 plus. So these octahedral coordination of Al3 plus and tetrahedral coordination of Be2 plus with 6 and 4 oxygens respectively, they lie between these rings of SiO4 tetrahedra. Now, in this position, they are linked to the oxygens of neighboring Si6O8 rings laterally and vertically. So you can see here that these oxygens to which these beryllium and aluminum ions are coordinated, they belong to the different rings of the tetrahedra, and they link with them laterally as well as vertically. So this structure results in a honeycomb. Now, other than this, the alkali beryls are also known, which have appreciable amounts of sodium and cesium. Sodium and cesium. So, if you see here, the central part of the rings, this is called as the channel site. This is called as the channel site. And sometimes these channel sites, they consist the sodium or cesium. in alkali beryl, sodium or cesium. This is not and, sodium or cesium. Okay, it can be found here and in large amounts in these vacant channels. So these alkali beryls, it it may contain alkalis up to 5 to 7%. And once these alkali beryls are linking up in that channels, they may sometimes tend to replace beryllium. Okay, so for the alkali beryls, you can have sodium, cesium, potassium, lithium, and it has been found that sodium and lithium and sodium, they can tend to replace beryllium, sorry, replace beryllium. So if you look at the chemistry of beryl, then the possible substitutions may be 3Be2 plus may be replaced by 2 lithium plus Si4 plus. Then it could be Si4 plus, which may be Be2 plus 2 R plus. I'll just tell you what is R plus. Then Si4 plus may be replaced by Al3 plus R plus. Then Be2 plus Si4 plus, it may be replaced by 2Al3 plus. Now, here the R plus, R plus could be, it could be a divalent or a trivalent cation. If it is R3 plus, then it would be aluminum, ferric, chromium, etc. If it is a divalent R2 plus, then it could be ferrous, it could be manganese, it could be magnesium. All these can be present in while the substitution goes on. An end member component, Famac beryl, has been found out. Famac beryl. The composition of the Famac beryl has been given as sodium, potassium, cesium, then Be3, R2 plus, R3 plus, Si6O. So R2 plus here, as I have already told you, it will be Fe2 plus or Mn or Mg. R3 plus would be aluminum, Fe3 plus, chromium, etc. So this is how the chemistry of beryl varies once the various types of ions place themselves in it, and has, as I have already mentioned previously, that the beryllium and aluminum, they coordinate in tetrahedral and octahedral coordinations respectively. A classification of beryl was proposed, and this classification, it proposed four types of beryls. So these are, first one is alkali free beryl. Here the total alkali is less than 0.1 weight%. The second one, the second type of beryl, it is alkali poor potassic and sodipotassic. beryl. As the name suggests, in this, potassium is predominant. Potassium is predominant, and here it ranges between 0.5 to 1.0 weight percent. Third type of beryl is sodic beryl. The sodic beryl, as the name suggests, has sodium predominant in it, and its weight percent will also vary between 0.5 to 1.00%. And the fourth type of beryl is sodic lithium beryl. Sodic lithium beryl. So again, here sodium will be between 0 to 2.0 weight percent, while lithium, the name is sodic lithium, so lithium will be less than 0.6 weight percent, while cesium here will be low. So these four types of beryls, they have been classified on the basis of the concentration of the alkali metals. Okay. All right. So moving ahead, as have been previously mentioned, that beryl can be synthesized hydrothermally. So it's a type of a hydrothermal deposit. It can be synthesized hydrothermal synthesis. And here it is synthesized from a mixture of SiO2, Al2O3, and BeCO2. So this mixture can lead to the formation of beryl at pressures which will vary from around 400 to 1500 kilobar and temperature at approximately 400 degrees Celsius. At 400 degrees Celsius, the beryl appears as fine white powder, while at 600 degrees Celsius, they appear colorless. This is how it has been all studied. The most common alteration product, the most common alteration product of beryl is kaolinite along with small amount of muscovite. Okay, and once we come to the paragenesis, so the beryl and aquamarine, they are they occur characteristically in wugs. Once you go through the ore geology and read the book of Bateman, Mineral Economics by Bateman, there they have given beautifully the different types of cavity filling deposits and hydrothermal deposits. There you will come to know about wugs, druses. Okay, so these wugs and druses, which are present in granites, granitic pegmatites, there the beryl and aquamarine commonly occur. The other associated minerals with beryl, they include quartz, feldspar, muscovite, lepidolite, topaz, tourmaline, spodumene, cassiterite. You can see You can now find different types of ores as well, and tantalite. These are the commonly occurring minerals along with beryl. The occurrence of beryl in granitic pegmatites, it is related to the size of the beryllium ion. Okay, the smallness, the because beryl is too small. So the smallness of beryllium ion that governs why this beryl occurs in granitic pegmatites. Now, the size of beryllium ion, it it causes the beryl to occur in granitic pegmatites. Now, what happens here? The beryllium, it gets concentrated in residual magmatic fluids. This is a very important thing, that beryllium gets concentrated in residual magmatic fluid. You all are aware about the primary and secondary magmatic processes. So the beryllium gets concentrated in residual magmatic fluid. And why? This is because this is because it cannot substitute in silicate structures, because beryllium can't substitute in silicate structures. And why is that? Because of its small size. Okay. Other than this, beryl has also been found to occur in some nepheline nepheline cyanides, in some mica schists, and sometimes in marbles as well. Okay, so this is in short about the paragenesis of beryl. So once you get questions on the structure, composition, and the paragenesis of beryl, let us say in GSI exam, so this is enough what you get in this video. The most important thing over here is to understand how the structure of beryl is formed, wherein you should go through this diagram, and you should understand that here we are having the rings, wherein the uh, oxygen and silicon, they are forming in a star-like structure. Remember that star-like structure, along with the beryllium and aluminum coordinations. Try practicing this diagram, is very easy. And suppose that you get this diagram to be a bit difficult, use this diagram. Is this much more simpler than the previous one. So here you can see yourself how you can see two overlapping rings of silica tetrahedra. So here you can see that those star structures are being formed that lead to the channel sites, and then you have the beryllium tetrahedron and aluminum dihedron. So I think this is a pretty simpler diagram. Post me any questions you have. Thank you.